Hey guys, so we can definitely say that binomial expansions is not the hardest topic that shows up in IB Math. And by the way, this is a common topic for both the SL and the HL courses. However, there are a few types of binomial expansions problems or exercises that you need to know how to go through. In the beginning, it does sound a little bit easier. However, as the topic progresses, there may be some sort of type of exercise that you might not be super comfortable with, especially two types, especially the ones that involve a term in the middle of a sequence, which you need to find specifically so you don't have to expand the whole thing, and also exercises that involve a power of n, so a binomial to the power of n. So we don't know the power of the binomial. These are usually the trickiest types of exercises. And the idea of this video is exactly that. Start with the easier types and progress our way towards the hardest one. Also giving you a brief intro to binomial expansions. So the exercises that we're going to work with are the following. Exercise number 0, which is actually not something that you're going to find in an IB exam, so that's why I labeled it 0. Expand 2 minus x to the fourth, but this will serve as a nice little intro for discussing binomial expansions. Now, mentioning the ones that can actually show up in an IB math exam. Find the term next to the fifth in this binomial, that's exercise number 1. Then find the coefficient of the term in x squared for this other binomial, which is a very similar exercise to exercise number 1. The difference here is that we're not addressing or finding the term, but the coefficient. But in practical terms, the difficulty is equivalent. This is one way also to go through a couple of examples of this type. This is a very important type. It's one that shows up a lot. And then we move to exercise number 3, which is to find the term in x to the negative 3 in a combination of two binomials. So we have one binomial times the other one. Then we have this exercise number 4, which is a bit more creative. We need to address in it two specific terms in this expansion. And then lastly, we have another one which, as well as exercise number 4, exercise number 5 also deals with a binomial to the power of n. These last two exercises are usually the ones that students have the most trouble with. So let's just bite the bullet and go through all of these, starting with an intro. Now, one of the best ways that we can introduce the binomial theorem or binomial expansions is starting with Pascal's triangle. I'm going to write it in two different ways, and we're going to prove a few things as we go along. The two different ways are one using integers and the other one using binomial coefficients. How do we build Pascal's triangle? In this row, which is called row number 0, we have a 1. In row number 1, which is actually the second one that we write, we have a couple of 1s over here. Again, we're going to explain where this comes from in a minute. Let's just go through the process first. On the row number 2, which is the third one that we draw, that we write, we have 1, 2, 1, and we create or we define these coefficients as the sum of these diagonals. So for example, this 2 is the sum of this 1 plus 1. And we continue with this pattern. We have, for example, a 3 here, which is the sum of 2 plus 1. The edges, or the first and the last coefficients, they're always 1. And we carry this process from top to bottom. I'm going to stop here at row number 5, which is actually the sixth one that we write. And I'll label them right here. This is row 0. This is row 1. This is row number 2, and so on and so forth. This 0, 1, and 2, and 3, and 4, they are associated to the power of the binomial that we're expanding. When we expand a plus b squared, for example, and let me do this one manually, or not manually, but actually writing the binomials and foiling, we get a squared plus ab plus ba, which is the same thing as ab, so we have 2ab, plus b squared, where the coefficients 1, 2, and 1 can be found in Pascal's triangle. We're going to mention why that's the case in a minute. Now, we go through the same process when expanding, for example, a plus b cubed, but this time we're not going to do this through foiling. This process becomes a burden when the power is greater than or equal to 3. It starts to be a hassle, right? So that's why, and this is one of the reasons behind using Pascal's triangle when expanding these binomials. So if you were to expand a plus b cubed, instead of getting the coefficients 1, 2, and 1 over here, like we did for a plus b squared, we would have the coefficients 1, 3, 3, and 1, as we see in Pascal's triangle. Now, for reasons to be mentioned in a minute. Now, this solves the problem for the coefficients, but it doesn't address how we can write or lay out the powers of a and b. And what we do is the following. We start with the highest, and by highest, I mean the exponent of the expansion power of a, and we decrease it by 1 as we go from left to right. If you do this from right to left, it works as well, but we're doing this from left to right. So let me just decrease a by 1 as we go from left to right. So a cubed becomes an a squared, becomes an a to the first, which becomes an a to the 0, which is just 1. We put the plus signs over here, and then we do the opposite for b. For b, we're going to start with the highest power, or the exponent of the binomial. But now, if we did a from left to right, we're going to do this from right to left. So b cubed, b squared, b to the first, and then b to the 0. Now, again, b to the 0 and a to the 0, these are just 1. A to the first and b to the first powers, they can be just written as a and b respectively. So our expansion becomes this. Now, why does this work, right? It seems like black magic, right? And it works for a reason to be mentioned after writing this triangle, Pascal's triangle, in a different way. If we write it using binomial coefficients, the explanation makes a lot more sense. Okay, so we're going to, next to these integers 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on and so forth, write the binomial coefficients that's actually represented, or that represents this integer. When writing the binomial coefficients, do know that we start with the row number and the number of the term minus 1. So for example, this is 0, choose 0. That's how we read it, which means that this is the first, or associated to the first term in row number 0. This, for example, is 1, choose 0, which means that this is associated to the first term in row number 1. Then we have 1, choose 1, and so on and so forth. Now, one thing that we still need to address, because we didn't mention yet, and I'm going to do this until row number 4, is how to go from, for example, let me just do one more over here, 5, choose 2 to 10. And this is something that we do a lot in probability and combinatorics. We're trying to find the number of ways of choosing k items from n available items. Let me place the formula here first. So this is n factorial over k factorial n minus k factorial, which means for this particular example that 5 choose 2, it is equal to 5 factorial over 2 factorial times 5 minus 2, which means 3 factorial. Now, what is a factorial again? N factorial means n times n minus 1 times n minus 2 all the way to times 1, which means that this is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and 3 factorial is 3 times 2 times 1. We can cross out a few numbers here. We can simplify the 4 with the 2, which becomes a 2, and everything is reduced to 10. 10 is the result. There's a simpler way of simplifying these factorials. If you rewrite, and let me place this here, this 5 factorial as 5 times 4 times 3 factorial, given that 3 factorial is the remaining 3 times 2 times 1, and knowing that 2 factorial is just 2, we could simplify it like this. And of course, we would get the same number, the same 10. So this is how we find and choose k. And do remember the definition where this comes from. This is the number of ways we can choose k items out of n. So let's say you have, and by the way, in this case, the order doesn't matter, okay? Let's say you're forming a group of 3 people out of 5 available people. And nobody occupies a different role. Everybody occupies the same role. So the only thing that matters is what group are we forming? We are forming, right? So if you have 5 available people and you want to make a group of 2, in this case, I'm going to use 2, okay? So from 5 people, there are 10 different ways of forming pairs or forming groups of 2, right? This is exactly what 5 choose 2 means. And this ties back to the whole idea behind Pascal's triangle. And this is the most important part. Why is it the case that when expanding, for example, a plus b to the 4th power, we have 6 different ways of choosing 2 a's and 2 b's? Well, we can see that if we draw a small diagram. So what is a plus b to the 4th? This is a plus b times a plus b times a plus b times a plus b. Well, it says here that we should have 6 different ways of selecting 2 a's and 2 b's when foiling, right? Which means that there are 6 different ways of choosing 2 a's from anywhere from here and 2 b's from anywhere from here. And do notice that you can only select either an a or a b in the same or in each binomial to compose that a squared times b squared. So for example, one alternative could be selecting these 2 b's and these 2 a's. And I'm going to copy and paste this a few times because I know that there are going to be 6 possible ways to get that. And the ways are BB, AA, BA, BA. And then if you play with this, you get 6 possible combinations in this foiling process. And this is where this idea of choosing is coming from. Given that this 6 is our 4 choose 2, 2 out of these 4 factors contribute with a B, and the other 2, 4 minus 2, contribute with an A. There are 6 possible ways of doing that. Now, the last thing that needs to be addressed or answered is the following. Why is it that the sum of these 2 diagonals produce this coefficient in the middle? Well, this comes from Pascal's rule, which states that n minus 1 choose k minus 1 plus n minus 1 choose k equals n choose k. Now, do notice that we're adding 2 numbers from the previous row. So, for example, 2 choose 0 and 2 choose 1. So these 2's, they're from the previous row. The sum of them, and k in this case being equal to 0 makes k plus 1 be 1, is equal to the term or the coefficient in the next row, which in this case is 3, choose k. So in our example, n equals 3 and k equals 1. Now, how can we prove this? We can use the definition of a binomial coefficient to write this as n minus 1 factorial over k minus 1 factorial times n minus 1 minus k minus 1 factorial plus, and then we have the second one here, n minus 1 factorial over k factorial, n minus 1 minus k factorial. Now, notice that this is the same as n minus k, in this case, n minus k factorial. And this can be rewritten as n minus k minus 1 factorial, just organizing the terms a little bit. We can copy these fractions again. And by noticing that k factorial is the same as k times k minus 1 factorial, when we reduce the integer by 1, we are moving to the next term in this factorial. So, for example, in this case, n factorial can be written as n times n minus 1 as times n minus 2 and so on and so forth. Or you can pretty much just stop anywhere and place a factorial in the end, because for example, in this case, this n minus 2 factorial represents the continuation of these products, n minus 2 times n minus 3 times n minus 4 until 1. And we can do something similar over here. This n minus k factorial is n minus k times n minus k minus 1, one iteration more, factorial. And this is going to allow us to write everything under the same denominator, which will be k times k minus 1 factorial times n minus k times n minus k minus 1 factorial. Therefore, in the numerator, we'll have the first n minus 1 factorial multiplied by k plus the second n minus 1 factorial multiplied by n minus k. Notice as well that k times k minus 1 factorial, doing this in reverse now, is equal to k factorial, and n minus k times n minus k minus 1 factorial is equal to n minus k factorial. Also, if you put n minus 1 factorial as a common factor in the numerator, we'll get this n minus 1 factorial times k plus n minus k. So this k over here plus this n minus k over here. The k's cancel out, and in the numerator we get n times n minus 1 factorial, which is just n factorial. And this is precisely the definition of n choose k. All right, so let this serve as an intro to binomial theorem or to binomial expansions.